Okay, just as there's standard error of the estimate, there's also standard error of our regression parameters. So the first regression parameter that we're going to talk about is B, because that's the first one that we calculated. So the standard error of B tells us how much uncertainty we have or lack of precision we have with estimating B. And here's where the standard error of estimate comes in, because the standard error of estimate turns out to be the numerator when calculating the standard error of B. So up here you can see we calculated the standard error of estimate by that simple formula that looks complicated, but really what it is it's the sum of the squared residuals divided by the degrees of freedom, and then we take the square root of that so we can have it in a metric that is in y units. The standard error of B is similarly estimated, but first we have to take into consideration the uncertainty of our model, and then what we have to take into consideration is the variability of x times degrees of freedom for calculating B. And degrees of freedom for calculating B is just n minus 1. So you can see that when I calculate this, and then I show you what the summary is of our LM1, if you look at the bottom here, you'll see that now I'm going to do SB, and you can see that SB is 0.6904 and then change, right? So here's our B, and there's the standard error of B. So what is that telling us? That's telling us the uncertainty of our parameter estimate B, taking into consideration how well the regression model as a whole functions, right? Because that's the standard error of our estimate, along with the variability. So it's the standard, it's the performance or precision of our overall model. That includes both B and A. But then we divide the standard error of estimate by what amounts to be the standard deviation, because we're taking the square root of the variance, and remember variance is just standard deviation squared, but then we're multiplying it by n minus 1. So what is that telling us? That we are getting a standard deviation along with however many degrees of freedom in our denominator. So the more variable we have of x, the greater the smaller the standard error of B. So we want lots of variability of x, and also consider sample size. If we have a huge sample size, the standard error of B goes down as well. And that's just all looking at this equation right here and parceling out each piece. So we have the standard error of the estimate in the numerator, and then the denominator we have the square root. Remember, that's taking the units back into y units, right? So this, or in this case, units that are part and parcel of our model. So what we have is the square root of the variance of x, right, times our degrees of freedom. And each one of these pieces gives us a little bit of a hint about the precision of our estimate for B. So if we have a poor prediction model, that is, we have huge residuals, we go back up here, the sum of our squared residuals, if that's really big, then our standard error of estimate is going to be really big. And that means that our standard error of B is going to be big because it's right here. However, it can be offset by having a large variability, so high variance in x, and also a large sample size. So a large sample size offsets a lot of the error in our models. So the standard error of B tells us how precise, how well is our B performing. And we're going to talk about hypothesis testing later, but standard error of B is critical in doing hypothesis testing to determine whether B is significantly different from 0. Again, we're going to get to that later. The next video is going to be on the standard error of A, which I'm going to get to in just a little bit. But just as a reminder, the standard error is calculated, and it's right next to, here's our estimate, 0.7, and our standard error is 0.69.